I will begin by orienting the viewers of the different statistical symbols. It will be followed by knowing the considerations in identifying the appropriate tools used in research analysis. And then I will discuss on the considerations to choose from in which statistical tests will be conducted. These are either descriptive or inferential, depending on the nature of the research. In order to come up with answers to research questions, the collected data need to be analyzed with appropriate statistical tools. All these tools use some symbol one way or the other. Some of the common statistical symbols are the following: a capital N to represent the population size, whereas a small n to represent the sample size. The mean of a population, we can use the symbol mu, and X bar for the mean of a sample. Population variance uses the symbol sigma square, and S square for sample variance. For both population and sample median, we use mid, and for the standard deviation of a population, sigma is used, whereas S is used for the standard deviation of a sample. We also use the summation symbol and alpha symbol to represent the level of significance type 1 error. The advancement of computer technology has made statistical analysis of data much faster and easier. In the past, it took days or even weeks to perform statistical computations for collected raw data from research. With the use of Excel, SPSS, Microstat, or other statistical programs, statistical analysis can be done in hours. But whether the data are analyzed with the use of computer programs or manually by calculator, the researcher needs to understand statistical tools and their applicability in research data analysis as basis for interpretation of results. The selection of the appropriate statistical tools depend on two factors. Number one, the question or problem statements of the research. That is, a descriptive question needs to be analyzed with descriptive statistical tools, while an inferential question needs inferential statistical tools. Number two, the measurement level of the collected data from nominal, ordinal, interval, or ratio level. The following are the common choices for statistical tools. Under the descriptive statistical tools, to measure the central tendency, the mean or the median can be used. To measure the variability, range, variance, and standard deviation tools are used. For the inferential statistical tools, there are the hypothesis testing, the one-tailed and two-tailed tests, the level of statistical significance, which include simple sample tests like the chi-squared goodness of fit test and the t-test for single population. There are the two related samples like the McNemar change test and the t-test for related samples. Then we have the two independent samples using the t-test for independent samples and the chi-square. Under the k-sample case, two options are the one-way analysis of variance or the ANOVA or F test and the Friedman two-way analysis of variance of ranks. For the measurements of relationship, we have the Pearson product moment correlation coefficient, R, or the Pearson rho. Descriptive tools are characteristics of samples or populations where complete data are available. They are indexes that summarize or describe a set of data. And the descriptive tools are the measures of centrality, dispersion, and association. The measures of central tendency or centrality are tools that are used to indicate a central value in a set of raw data. These are the mean, median, and mode. The mean is a central value that is computed by getting the sum of all the observations divided by the number of observations. It is also called arithmetic mean or average. The population mean is mu, while the sample mean is x bar. To illustrate, the GPA of 7 research students were 2.5, 1.75, 2.0, 1.33, 2.20, 2.05, and 1.88. The sum of all these GPA are then divided by 7 to come up with a mean of 1.958. The properties of the mean are the following. Number 1, all observations contribute to the value of the mean. 2, the higher the mean, the higher is the magnitude of the raw data. For example, if the mean income is high, it means that the respondents have high income. Third, the mean is easily affected by extreme values, like an extremely low or high value. Because of this weakness of the mean, it is not a good indicator of centrality when there are extremely high or low values. And lastly, means of subgroups can be combined to yield a weighted mean. For example, Section X with 30 students has a mean rating of 91, while Section Y with 33 students has a mean rating of 88, and Section Z with 35 students has a mean rating of 89. Our total population, therefore, is 98. So the mean of Section X, which is 91, multiplied by number of students of Section X by 30, is added to the mean of Section Y of 88 multiplied by the 33 students, and add that to the mean of Section Z of 89 multiplied by the 35 students in Section Z, all divided by 89, or the population of the sample, to come up with a mean of 89.2275. The median is a central value that divides a set of observations into two equal parts, such that 50% fall below it and 50% fall above it. Finding the median requires you to arrange the data into an array. An array is an arrangement of data from lowest to highest or from highest to lowest. Next, to determine the median by the formula. Xn plus 1 all over 2 is used if the sample size is odd, and xn over 2 plus xn plus 1 over 2 all divided by 2 is used if the sample size is even. The first table on the left shows the grades of 9 students, wherein student number 1 got an 81, student number 2 83, up to student number 9 who got 93. Since the sample size is odd, the formula is xn plus 1 over 2. Substituting the values, it is x9 plus 1 equals to x10 all over 2, getting the median of x5. x5 has a corresponding grade of 87, which makes it the median. The table on the right shows an even number of population. Therefore, the second formula is needed to be used. It's x10 divided by 2 plus x10 plus 1 divided by 2, coming up with x5 plus x6 all divided by 2, or the grades of x5, which is 87, and x6, which is 89, divided by 2 to come up with the median of 88. Two of the properties of the median is that 1, not all observations contribute to the value of the median. Only the middle value if the sample size is odd, or two middle values if the sample size is even in an array are involved. Next, the median is a positional value and therefore is not affected by extreme values. In example 2 given earlier, even if the lowest rating is 75 or the highest rating is 99, the median is still 88. Because of this property, it is more reliable indicator of centrality when there are extremely high or low values. Mode is the most frequent repeating value. It is the observation with the highest frequency. On the table on the left, there are 12 sample populations with scores ranging from 81 to 93. Arranging the data into an array, we could determine the number of times a certain data is repeated. Here, the data of or the grade of 84 has been seen to be repeated 3 times, making it the modal rating with the highest frequency of 3. Measures of variability are the tools to determine how dispersed are the set of data. They are also called measures of dispersion or variation, and these are range, variance, and standard deviation. Range is the distance or difference between the highest and lowest values. It is represented by the formula R, or range, is equal to HV, or highest value, minus LV, the lowest value. Its properties include is that range involves only the highest and lowest values, and thus is easy to determine. The higher the range, the more dispersed is the set of data, and the lower the range, the less dispersed is the set of data. If the range is 0, the data are not dispersed at all. Because it emphasizes the extreme values, it is the most unstable or unreliable measure of variability. Its value easily changes or fluctuates with the change in extreme variances. Variance is the average of the squared deviations of each observation from the mean. It is an indicator of how much variability there is in an entire distribution of values. Its properties, one of its properties is that it reflects the dispersion or variability of the data. That is, the higher the variance, the more dispersed is the set of data, and the lower the variance, the less dispersed is the set of data. Second, it is expressed as squared unit of measurement of the raw data. This is the weakness or disadvantage of the variance. Because of this weakness, there is a need to get its square root. The formula for population variance, sigma square, is equal to the sum of the difference between x bar and the data point squared, all divided by n, where n is the number of samples. In the case of sample variance, it is x squared is equal to the sum of the difference of x bar and the data point squared, all over n minus 1. A sample computation to determine the sample variance is as follows. The table on the middle gives the data points. So the first step is to determine the summation of the data points. We have 91, 93, 90, up to the last data point of 87, the sum of which is 1,130. Next is to determine the sample size. In this case, we have 13 samples. All we need now next is to determine the mean. So it is 1,130 divided by 13 to come up with the mean of 86.9. The next column shows the mean is being subtracted from the data point. So it is 86.9 minus 91 to come up with a difference of negative 4.1, and 86.9 minus 93 to come up with a difference of negative 6.1. And we continue until the last data point. Next step, part of step 2 is to square the difference. So negative 4.1 squared is 16.81, and negative 6.1 is square is 37.21. The sum of all the squared differences is 126.93. Now, substituting it with the formula for sample variance, S squared is equal to 126.93 divided by 13 minus 1, or 12, to come up with a sample variance of 10.5775. Standard deviation is the square root of the variance. It is an indicator of how far the data are from the mean. The simplified population standard deviation is sigma is equal to the square root of sigma squared. And for the sample standard deviation, it is S is equal to the square root of S squared. The properties of standard deviation are as follows. Number one, like the variance, the standard deviation reflects the variability or dispersion of the data. That is, the higher the value, the more dispersed is the set of data, and the lower the value, the less dispersed is the set of data. In other words, if the standard deviation is small, the values are clustered tightly about the mean, and if the standard deviation is large, the values are scattered about the mean. Number two, the standard deviation is expressed in the unit of measure of the raw data. This is its advantage over the variance. If the data are ages of research subjects, a standard deviation of 3.25 means that the ages differ or deviate from the mean age by 3.25 years. Inferential statistical tools are concerned in making generalizations about the population basing on observation about the samples. It is carried out by conducting hypothesis testing, either by one-tailed and two-tailed tests or by tests to determine the levels of statistical significance. Here is where the different tests fall under. In Chapter 2 of the research, the statements of the problem in research may be descriptive or inferential problems. Inferential problems need to be analyzed with inferential statistical tools. Statistical analysis for inferential problems consists of testing hypotheses. A hypothesis is subject to statistical testing to determine whether it should be accepted or rejected. How the alternative hypothesis, or HA, is formulated determines the type of test to be used in hypothesis testing. A one-tailed test is used when the HA is directional, which means that the value of the measures is greater than or less than the other measure. A one-tailed test is a hypothesis test for which the rejection region lies at one tail of the distribution, whether left-tailed test or right-tailed test. If the sample mean is less than the specified value, then it is a left-tailed test, for which the HA is stated. A two-tailed test is used when the HA is non-directional, which means that the value of two measures of the same kind are not equal. It has a not equal sign in the alternative hypothesis. To illustrate the difference between a one-tailed and a two-tailed test, consider the table below. For a population type of a single population, and where the hypothesis says that the sample mean is less than 83, the test type would be a left-tailed. If it is a two sample or two population, and the hypothesis states that the mean of private school students is less than the mean of public school students, then the test type is left-tailed. If the population type is a single population and the hypothesis states that the sample mean is greater than 83, then the test type would be a right-tailed. Where there are two samples and population, and the hypothesis states that the mean of private school students is greater than the mean of public school students, then the test type would be a right-tailed. If the population type is a single population, and the hypothesis states that the sample mean is not equal to 83, it is a two-tailed test type. And where the two samples or population, where the hypothesis indicates that the mean of private school students is not equal to the mean of public school students, it is a two-tailed test type. In testing the hypothesis, consider the following procedure. Number one, Formulate the null and alternative hypothesis. 2. State the decision rule, which includes the level of significance, the test statistic, and the critical region. The direction rule is the basis for the decision. Number 3. Compute the value of the statistical test. Fourth, decide whether to accept or reject the null hypothesis basing on the decision rule and the computation. And lastly, draw the conclusion basing on the decision. The value computed using the statistical test will be compared to the critical values of the applicable table of the test used. Depending on the decision rule raised by the researcher, the computed value and the corresponding critical value based on the decision rule is compared. This helps the researcher in determining whether to accept or reject the null hypothesis. The following are sample tables of the different critical values of commonly used statistical treatments. We use the chi-square distribution test, the Friedman two-way analysis of variance by ranks, the student's t-test distribution, and the f-test distribution table. In making conclusions from statistical analysis, there is a need to select the level of statistical significance, which is denoted by the Greek letter alpha. The significance level of a test of hypothesis is defined as the probability of committing a type 1 error. This is the probability of rejecting the null hypothesis. The zero point zero 0.05 level of statistical significance means that the probability of error in rejecting the null hypothesis is 5%, but 95% sure that the decision made is correct. In other words, an obtained result that is significant at the zero point zero 0.05 level could occur by a chance of only 5 times in 100 trials. The zero point zero 0.01 level means that an obtained result could occur by chance only once in 100 trials. The zero point zero zero 0.001 level means that an obtained result could occur by chance only in 1,000 trials. Social researchers commonly use the zero point zero 0.05 level, while biological and medical researchers use the zero point zero 0.01 or zero point zero zero 0.001 because recommendations from findings in medical researches should be based on the lowest margin of error. The chi-square test, or the chi-square goodness of fit test, is used to determine whether there is a statistically significant association between the two categorical variables. In business research, this technique is used to determine if the relationship exists between any two business parameters that are of categorical data type. One might use this technique to determine whether gender is related to a voting preference or whether the two data points are independent and unrelated. Or an enterprise might also use the chi-square to determine if there is a relationship between the region in which a product is purchased and the product or category of product that is purchased. In marketing or market research, the chi-square is used to determine if certain types of products sell better in certain geographic locations than others, and to verify if gender has an influence on purchasing decisions. It might be used to identify if there is an association between income level of consumers and their choice of brand. To determine if customer age has an influence on product or service subscription, assuming age is converted into age brackets such as 18 to 25, 26 to 35, etc., this technique is helpful in finding a relationship between any demographic characteristic of consumers or research respondents for education, location, gender, and etc. Various preferences, perspective, behavioral attributes such as entrepreneurial characteristics or product service preferences or career preferences, income level, political party preferences, and etc. For politics or election time, a marketing research may want to know if gender has an influence on political candidate or party preference. The chi-square test, or the chi-square goodness of fit test, is applicable for analyzing a number of responses under various categories. It is concerned in finding out if observed frequencies are in accordance to expected frequencies. The chi-square goodness of fit test is applicable for nominal data. The following is the formula for chi-square test. The sum of the square of observed minus expected frequencies divided by the expected frequencies. A critical table of chi-square values is used in comparing the computed value and the critical value based on the parameters of the decision rule to come up with a decision of whether to accept or reject the null hypothesis. Consider the following as an example of the chi-square test. In a socio-economic survey, a researcher wanted to find out, at 0.05 level of significance, if the occurrence of low, average, and high income groups follow the 4:3:1 ratio. From a total of 160 research subjects, he found out that 100 belonged to the low income group, 40 belonged to the average income group, and 20 belonged to the high income group. The first step is to formulate the null hypothesis, which is the occurrence of low, average, and high income group follows the 4:3:1 ratio. And to formulate the alternative hypothesis, the occurrence of low, average, and high income groups does not follow the 4:3:1 ratio. Second step would be to come up with the decision rule. It is to reject the null hypothesis if the chi-square computed is greater than the critical value of the chi-square table test based on the parameters. Otherwise, accept the null hypothesis. And the third step is to do the computation for the chi-square. The formula for the chi-square test starts with getting the sum of the ratio of 4:3:1 is equal to 8. Now, number 2, get the probability of each cell by dividing each term of the ratio by the sum. So it will be 4 over 8 is to 3 over 8 is to 1 over 8. Third step of the procedure is to multiply the probability of each cell by the number of samples. In this case, 4 over 8 multiplied by 160 for low income to come up with 80. For middle income, it is 3 over 8 times 160 resulting to 60. And for the high income, it is 1 over 8 times 160 equals to 20. Tabulate it under expected, then sum it up, and compare it with the observed numbers and sum it up. Computing for the chi-square test is as follows. Sum the squared difference between the observed frequency and expected frequency and divide it by the expected frequency. Do this across all income groups. So in this case, the square of 100 minus 80 divided by 80 for the low income group, 40 minus 60 squared and divided by 60 for the middle income group, and 20 minus 20 squared divided by 20 for the high income group. All of this will come up with a computation or a computed chi-square of 11.67. Next, based on the decision rule parameters of 2 degrees of freedom at 0.05 level of significance, we come across a critical value of 5.99. Now, since 11.67 is higher than 5.99, we therefore reject the null hypothesis. And our conclusion would be that the distribution of the research subjects does not follow the 4:3:1 ratio. The t-test assesses whether the means of two groups are statistically different from each other. This analysis is appropriate whenever you want to compare the means of two groups, and especially appropriate as the analysis for the post-test only two-group randomized experimental design. The graph shows the distribution for the treated, the one in blue, and control, the one in green, groups in a study. The figure indicates where the control and treatment groups means are located. The question the t-test addresses is whether the means are statistically different. The t-test is also called the student's t-test, derived from the fact that it was developed by a student of Fisher, a well-known statistician. This statistical tool is applicable for data in at least interval level. It is used to find out if an observed mean differs from an expected mean. For a two-tailed test, the null hypothesis would state that the sample mean is equal to the population mean, and that the alternative hypothesis states that the sample mean is not equal to the population mean. Therefore, the decision rule for a two-tailed test is that at the given level of significance, reject the null hypothesis if the t-value is greater than the critical t-value based on the parameters, and accept the null hypothesis if otherwise. To compute for the t-test for the two-tailed test, it is the t-value is equal to the mean of the sample minus the mean of the population divided by the sample standard deviation over the square root of the sample size. For a one-tailed test, the null hypothesis would state that the sample mean is equal to the population mean, and that the alternative hypothesis states that the sample mean can either be less than or greater than the population mean. And the decision rule would be at the given level of significance, reject the null hypothesis if the t-value is greater than or less than the critical t-value based on the parameters of the decision rule. As a sample application for the t-test for single population, consider the following. In a test designed to measure a person's ability to think logically, college freshmen should average 72.6 points. This test was given to a group of 30 college freshmen who have just completed a required course in mathematics, which is supposed to sharpen their general powers of reasoning. The students had a mean of 77.8 with a standard deviation of 10.8. Then, test the effectiveness of the course at 5% level of significance. This example is considered as a one-tailed test because the problem calls for finding out whether the course is effective and that the mean should be higher than 72.6. Based on the data given by the problem, the null hypothesis would state that the sample mean is equal to 72.6, and the alternative hypothesis would be that the sample mean is greater than 72.6. The decision rule would be to reject the null hypothesis if the computed t-value is greater than the critical value of t based on the parameters and which can be found on the t-test table. To compute for the t-test, 77.8 minus 72.6 divided by 10.8 over the square root of 30 to come up with the computed t-value of 2.6. Now, 2.6 is compared to the critical value of t as based on the table with a degree of freedom of 29 and a level of significance of 0.05 intersecting at the value of 1.6999. Therefore, the decision is that the 2.6 computed t-value is greater than 1.6999, and therefore we reject the null hypothesis. The conclusion would be it's that the alternative hypothesis is that the mathematics course is effective in sharpening the general powers of reasoning of the students. The McNemar change test is also called the within subjects chi-square test. It is used to find if there is a change in the respondents over time. It is applicable to researchers with a before-after design, where two responses are expected from each research subject. It is used for nominal data. The formula is that the prime a minus d minus 1 squared all over a plus d at 1 degree of freedom. And the decision rule for a McNemar change test is that to reject the null hypothesis if the chi-square is greater than or equal to x squared alpha at 1 degree of freedom. Otherwise, accept the null hypothesis. One, square that, and divide that by 32 plus 24 to get a computed chi-square of 0.87. Now, compare that with the 1 degree of freedom of the critical value and basing it on the chi-square table, we get a 3.84. We divide that by 2 to get an answer of 192. Thus, the decision is that since x squared is less than x squared alpha over 2 at 1 degree of freedom, the null hypothesis cannot be rejected. Therefore, it is thus accepted. The conclusion here is that the null hypothesis, or the number of respondents who change from negative to positive, is equal to the number of those who change from positive to negative. This means that the information drive was not effective in convincing rural folks to join the cooperatives. The t-test is designed to find out whether two conditions differ when the samples or observations under two conditions are related. That is, to find out if two related samples differ from each other. It is appropriate for data measured in at least interval level. It is used to determine if there is significant difference between two groups of correlated scores in terms of their means. It is useful for before-after designs of research, where a research subject or unit of analysis is measured twice. Selected student participants. The first group, 145 students from private schools, got a mean score of 88 with a variance of 45. The second group, 125 students from public schools, got a mean score of 90 with a variance of 35. To determine whether these results indicate that those from private schools performed better than those from public schools, conduct a test of hypothesis at 0.05 level of significance. This example would be considered a one-tailed test or one-directional test because the problem finds out if a private school student's performance is higher than the public school students. Thus, the null hypothesis would be that the private school students' performance is equal to the performance of the public school students. The alternative hypothesis states that the private school students' performance is better than the public school students' performance. Our decision rule would be to reject the null hypothesis if the computed t-test is greater than the critical t-test and accept the null hypothesis if it is otherwise. To compute, we get 145 minus 1, or 144, times 45 which is the variance for the private schools, minus 125 minus 1 or 124, which is the population of the public school students, multiplied by the variance of 35. Divide everything by the population of the private school students and the public school students minus 2 to come up with a computed t-test of 2.57. Compare that to the critical value of t-test given at 0.05 level of significance with a 268 degree of freedom to come up with the critical value of t-test of 1.96. Our decision would be to compare the 2.57 to the 1.96. Since 2.57 is greater than 1.96, we therefore reject the null hypothesis. And we come up with a conclusion that the alternative hypothesis that the private schools students' performance is better than the public school students' performance. The one-way analysis of variance, or ANOVA, or F-test, is a tool used to find out if three or more treatments or groups differ with respect to a variable. It is applicable to continuous data. It is a technique that considers the total spread of dispersion of data from several sources. In its simplest form, ANOVA is used to test the significance of the difference among three or more populations. It is also called F-test. The differences among means are evaluated by generating an F statistic, which is the ratio that compares the variation within the sample to the variation among samples. In other words, suppose a researcher compares the means of sample A, sample B, and sample C. Conducting an F-test is like conducting a t-test for independent sample means between sample A and B, B and C, and A and C at the same time. We assume the F-test to have random samples, that samples are independent of one another, and samples are from normal distributions, that true variances of each groups are equal, and the data are at least in interval level of measurement. The Friedman's two-way analysis of variance by ranks is a statistical tool applicable for k-related samples. That is, to find out if three or more related groups or treatments differ from each other. It is used when the data are in ordinal level. The following is the Friedman two-way ANOVA formula, where 12 is constant, 3n is constant, and capital N represents the number of subjects or respondents. As an example of the Friedman two-way ANOVA by ranks, consider the following example. In the process of evaluating three instructional methods, an educational researcher tried to determine whether the three methods differ in student evaluations. In order to remove the biases of the students, he considered only the students to whom the three methods were applied. Based on the results below, on the number of points given to each method, test at zero point zero 0.05 level of significance whether the three methods differ in student evaluations. Based on the table, we have 6 student participants who gave their grades or scores on the three methods A, B, and C, and we ranked the scores accordingly. Our null hypothesis here is that method A is equal to method B is equal to method C. Our alternative hypothesis is that method A is not equal to the method B is not equal to method C. Our decision rule is that at zero point zero 0.05 level of significance, we reject the null hypothesis if the Friedman computed is greater than or equal to the Friedman tabular. Otherwise, we accept the null hypothesis. Substituting the data with the variables in the formula, we get a computed Friedman of 7. And we search for the Friedman tabular with the population of 6 with a 0.05 level of significance. And we also find that the tabular Friedman is at 7. Our decision is, since Friedman tabular is equal to the Friedman computed of 7, we therefore reject the null hypothesis. Our conclusion is that the three instructional methods vary from each other and that the students do not have the same evaluation for the three methods. The Pearson product moment correlation coefficient R, or Pearson rho, is an example of measure of relationship. It is used to determine if there is a correlation between two variables. It is applicable for continuous data. It is sometimes referred to as Pearson rho because the correlation is indicated by the symbol R, which stands for rho. The value of R, or rho, changes from positive 1, which is perfect positive correlation, to 0, no correlation, to negative 1, or the perfect negative correlation. Positive correlation between variables x and y means that if x is high, y is also high, and if x is low, y is also low. Negative correlation between x and y means that if x is high, y is low, and if x is low, y is high. Zero correlation means that whether x is high or low, this has nothing to do with the value of y. Consider the following as an example of the Pearson rho. Is there a relationship between abilities in English and in math? Using the following data and basing on a 0.05 level of significance, test the null hypothesis that a student's ability in English is not related to his ability in math. The table shows the 6 student participants with their English scores under X with a mean of 35.5 and their math scores represented by Y with a mean score of 34. Then we get the deviates. It is the score of each student minus the mean score. For student 1, we have 41 minus 35.5. We get a deviate for X of 5.5. And for his math scores, it is 30 minus 34, and we get a deviate of negative 4. We then square the deviates. So the square of 5.5 is 30.25, and the square of negative 4 is 16. Lastly, we multiply the deviates of x and y. We get 5.5 multiplied to negative 4. We get a product of deviate of negative 22. We do these steps to all the rest of the 5 students. Our null hypothesis would be is that there is no significant relationship between the English scores and the math scores. And our alternative hypothesis is that there is a significant relationship between the English scores and the math scores. Our decision rule here is to reject the null hypothesis if the t-value is greater than or equal to the alpha over 2 with a degree of acceptance of n minus 2. We accept the null hypothesis otherwise. Substituting the formula with the variables or the data we got from the table, we get a t computation of t of 0.081. Now we look up at the table the value of alpha over 2 at 4, we get a value of 2.776. Our decision then is to accept the null hypothesis, since 0.081 is less than 2.776. Our conclusion, there is no relationship between the math scores and the English scores. That is the end of the report. The statistical tools may be complicated, but they are discussed further in detail under the course subject of Advanced Statistics, which we may refer to for further understanding. Thank you for listening.
This is Cheryl Arbues, and I'll be reporting about the presentation, analysis, and interpretation of data. The result section of an original research paper provides answer to this question: what was found? The amount of findings generated in a typical